All right. So today we're gonna talk about the Wilson-Fisher fixed point, and we start with a review of lecture 10, in which we discuss the Callan-Simanzi equation and the solutions to it. Here's the Callan-Simanzi equation as an equation for that correlators of the renormalized theory with renormalized fields and renormalized couplings will have to satisfy. This term tells you how the correlator depends explicitly as a function on the physical scale, mass scale in the problem, physical scale of interest. This is the dependence on the coupling. Beta functions are the running of the couplings, right? And these gammas are the anomalous dimensions, and n has to do with the endpoint functions. I'm assuming that these are the correlators of the same operator. Otherwise, you would sum over gammas corresponding to each operating insertion. These are wave function normalizations. We said that we treat mass as a coupling as well, because the whole structure of it is that we view quantum fields here as a deformation around the trivial fixed point. So there will be a coupling. This is a dependence on it, and this is the beta function, or the running of mass in Callan-Simanzi. It is always a relevant coupling, right? By the virtue of the mass that has the fact that the mass has dimension of mass. All right. Forgot my good chalk. I got some Hagar-Roma. So Callan-Simanzi is the statement that renormalized correlation functions change nicely, covariantly, or actually, if once you take the wave function normalizations into account, are invariant under these changes. All physical observables, including the S matrix and effective action, should also be invariant under this transformation. So if this is the S matrix, the total derivative, or there should be no total dependence on M. So it's dependence on M will have to cancel by the dependence of mass and couplings on M. Good. Similarly, effective action will satisfy an equation, Callan-Simanzi-like equation. Here there is an extra term which has to do with the variation with respect to phi classical. So this is for you guys to figure out why this term is there. Any thoughts? All right, you'll figure this out. Questions? All right. We talked about composite operators and anomalous dimensions. We said anomalous dimensions have to do with the fact that the z of phi squared is not the same as z of phi squared, right? So you need a brand new renormalization for composite operators that we define in the fixed point, trivial fixed point, using normal ordering. If you have multiple OPs and there's no symmetry forbidding mixing them, they in principle always mix. So what you see in the infrared is a mix of all the operators in the UV with a bunch of normalizations. So under RG, operators with the same quantum numbers mix. Right. Questions? In Callan-Simanzi, we introduced anomalous dimensions for these. If we write down Callan-Simanzi for these composite operators, we can. Then there will be anomalous dimension corresponding to them that is defined as as the dependence of MDDM of logarithm of the renormalization ZO of M. We saw that these under RG transformation, M goes to MB and X goes to X over B. That means the phi n under RG goes to phi n of X over B MB, B to the power of gamma of phi n, the anomalous dimension of phi n, plus n d classical. D classical is the classical dimension of it. So that is hence the name of anomalous dimension. All right. We also talked about, oh, no. Things get shifted. We talked about the solutions to Kalam-Siman's equation. We use an analogy of a bunch of bacteria flowing down a current stream. We define T as log of P over M. We wrote down an ansatz for G2 of lambda and used that to write massage Kalam-Simanzik in this form. In doing that, what we did was we traded M dependence for P dependence. What does that mean? It means that previously we were looking at correlators of fixed P changing M. Now we're fixing M and changing P because the dependence is only over P over M. Right? So that was the origin of that minus sign that I got confused about last time. So in the UV, you start with P equal M. This is T equals 0. And there will be some sort of a coupling, lambda bar of 0 and lambda that we call lambda. Right? Now you will have to solve the beta functions equation to find the running of the coupling as a function of scale. Right? I can interpret this again as the M dependence or P dependence, keeping M fixed. So this is the running, the beta functions and the running of the couplings. Once you find that, you plug that into your ansatz, right? And then we saw that the solutions to the rule of the anomalous dimension term was that it makes the operators grow in size, change in size, and it contributed this way. Do I need to repeat the analogy of the stream, or is that good? Good. Okay. It's called the method of characteristics for PDEs. It's a very famous method. Importantly, this was an ansatz, so we don't know what this function is. So we just formally wrote down a solution to the Kalam-Siman's equation, but we didn't really solve it. To really solve it, what you should do is that you should expand this in perturbation theory, order by order in perturbation theory. This is not a solution to anything because you don't know what G2 is. This function is to be determined. So the idea is that what you would like to do is you would like to calculate G2 of P of lambda in some expansion. And in the above equation, you know that, well, okay, so you just do this in perturbation theory order by order. So first order, you would do this in your homework. So basically, G2 of lambda bar at the 0th order, when T is equal to 0, when lambda goes to 0, this has to be 1. Right? Because the propagator is just minus I over P squared. The lambda is 0. So that's your condition. Then you expand it order by order. This is equivalent to, this integrated form is equivalent to what we were doing before. What we did before was that we first expanded terms in lambda. We expanded Kalam-Simanzik, the differential form of Kalam-Simanzik in lambda. It became an algebraic equation. Then we solved it. Here we formally integrated it. This formal integral form is equivalent to differential form, so we haven't done much. You will have to again do perturbation theory and expansion. Especially keep in mind that these integral forms are really useless if you cannot non-perturbatively integrate, right? This is just formal. It's very, very formal, but it does help you understand the structure of it. The size of the operator grows and the running of the couplings. Questions about this? So in your homework, I posted homework 3. You will do an example of renormalization of a composite operator. That Z of O. So some O of R. By size, I mean the wave function normalization. This guy. Half, sorry. By definition, we have this half. Yeah, the term size is not standard. I'm just making things up. I just don't like the word wave function or normalization. There's no wave function here. All right. So we did that for G2, the 2-point function. Now I'm just going to sketch how it will work for the 4-point function. Consider the connected 4-point function G4 in lambda phi 4 and choose the momenta. It's a function of 4 external momenta. We said that in Kalin-Szymanczyk, you always construct this mass scale, right? That mass scale in this example, I'm telling you, I'm making the following suggestion. Pick PIs, the 4 external legs, to be minus some capital P squared, some fixed value of P. And then pick Pi dot Pj equals 0. This is a choice that will correspond to saying that S is equal to T equal to U. Well, sorry, S, T, U are all, I don't know why this no longer works, are order minus P squared. I lost my pen. All right. So a question for you guys. What kinematic configuration is this? Right? You remember in scattering P and P prime, or P and K come and P prime and K prime go. S and T and U had to do with various P minus P prime or plus K prime, blah, 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 squared, right? In the center of mass, S is the center of mass energy squared, right? They also satisfied another relation. S plus T plus U was, I think in our notation, 2 mass squared, if they are the same particle. So this is a configuration that you have to look at. There's a point I have here. Do this. You'll discover something important. I'd already said this in a little bit of a different way. So when we talked about renormalization conditions, there are 2 types of renormalization conditions that I wrote down. One renormalization condition for lambda phi 4, we wrote down for the connected 4-point function. I said that you want this at S equal P squared, T equal U equals 0 to be minus I lambda. Right? This is what I did a while ago. Then when we were talking in our discussion of RG flow, I did something a little bit differently. I wrote S equal T equal M squared. I wrote P squared equal U. That's what I'm writing now. Minus or plus, whatever. Think about when you can satisfy this and why I changed that. All right. Does anyone have a guess right now? You have to just write it down, I think, but if you have an intuition for it, it will be good. To the leading order, G4 is I over P squared to the power of 4 minus I lambda. That should be clear, right? There are 4 external legs. Each of them will contribute minus I over P squared to the power of 4 minus I lambda. Minus I lambda comes from the connected, the amputated diagram. As before, we're going to write the ansatz, which is 1 over P8, some function, some curly G of P squared over M squared. This is some ansatz we can write down. So similarly, you can try to solve the Kalin-Szymanczyk formally by doing the same steps similar steps as before. You trade P for M, and you end up with the following form of Kalin-Szymanczyk. 1 over P8, some function that's to be determined. E to the power of 4, the 4 has to do with 4 insertions. Previously we had 2. I wrote this as not as an integral, well, it was an integral over dt, but I already wrote it in terms of M and P. At t equals 0, I took P to be equal M, and I'm keeping M fixed, changing P, right? So this is that dt. This function is not known, but of course you can solve for it in perturbation theory by doing the calculation of the 4-point function and the loop integrals. This is at the lowest order minus I lambda bar, right? So we need to expand lambda in perturbation theory and solve for this. Questions? All right, so that's a summary of what we discussed last time. Today, what we're going to talk about, in the remainder of the discussion of RG, we have 3 lectures, maybe 3. Maybe I'll cut it down to 2. We'll see. First, so the goal is to talk about explicit models that exist, that are useful in the real world. There are 2 examples that I'm going to give you, but these examples are classes of examples. These are very important classes of examples. There aren't many classes that exist. One is Wilson-Fisher. Wilson-Fisher fixed point of the ON model. So we're gonna solve. This is a very, very concrete calculation. Wilson-Fisher of ON model. There's a large class of these such theories. And if you're curious, there's a lot to learn here. Then the other class of is nonlinear sigma model. Both of them are 2 important classes, and there's a world of sigma model. ON model is a linear. You could call it linear sigma model as well. You could call it that way. But we're going to talk about nonlinear sigma model next time. These are examples in which we have a controlled deformation of an RG fixed point, and we end up with a quantum field theory, a flow that's fully well defined and understandable. In this case, in particular, you're going to see that you flow between 2 fixed points within perturbation theory. We're going to relate that to theories that we have discovered out there in the real world, and condensed matter theories, actually. And then the nonlinear sigma model is a whole different universe. We'll talk about that next lecture. That's where you use symmetry in a different way. Use symmetry in an interesting way to constrain the flow of your RG flow. I might or might not include a lecture on exact RG. So there's a last lecture on exact RG. I might suppress it. We'll see. All right. Is it clear what we're going to talk about? So today we're going to talk about the Wilson-Fisher fixed points of the ON model. All right. To do that, I'm going to rewind and go back to classical field theory and spin models. Back to condensed matter, statistical field theory. Imagine a bunch of spins. I'm drawing them there on a line, but they could be on an arbitrary dimensional lattice. Good? Okay. This theory, the degree of freedom is up or down. The Hamiltonian is nearest neighbor. The Hamiltonian has one symmetry, Z2, right? Because the terms that we include in the Hamiltonian are SI, SI plus SI. So the Hamiltonian, well, oh, and now it's writing, good. These are nodes that are connected. It doesn't even have to be a lattice, but so if you flip each S to minus S, it's a symmetry. So it's a Z2 symmetry. That should already tell you that it smells like free scalar field. Not quite, but there's a Z2 symmetry that we're going to keep track of. The spontaneous symmetry breaking here is also going to be about Z2. Okay, good. So put this in some external field. So put the phi temperature in some external field that sources spin, magnetization, some magnetic field. We're going to calculate the 2-point function, the connected 2-point function, and then there will be a critical temperature in 1 plus 1, sorry, I should say, this is a statistical field theory. In 1-dimensional spins, what is the setup? The 0 temperature vacua are, there are 2 of them. There's spontaneous symmetry working, right? It's all up or all down. There's no phase transition. Any non-zero temperature breaks or restores order, right? So there's no phase transition. Good. In 2 dimensions, the Ising model. Do you guys know what the deal with to the Ising model is? What is the theory? It's exactly solvable using the Onsager ansatz or whatever. You solve it explicitly. We know exactly what it is. There's a phase transition, finite temperature phase transition. It's a continuous phase transition. The 2-point function takes this form. There is an anomalous dimension here. What does this tell you? 1 over x to the power of d minus 2. Well, first of all, it looks like conformal fields here, but also this looks like 2 scalar fields, right? Because the dimensionality of scalar field was d minus 2 over 2, the insertion of that. And if you remember, actually, that when we related the spin model to scalar field, we actually saw how it comes about, right? You average these spins on large regions and it becomes a real scalar field, which is the average of it. That's actually a phase. It's a compact scalar, blah, blah, blah. So something that could be filled in. These are some critical exponents. These are called critical exponents. You see them in real life, right? Away from the critical point, G2 takes the form of e to minus x over c. This is called the correlation length, right? The one way of defining continuous phase transition is the fact that correlation length blows up, right? How does correlation length blow up? T is the how far away from, it's a dimensionless parameter about how far you are off of the critical temperature. This blows up as with a critical exponent nu. So far there are 2 exponents in this. Yeah.
So correlation length, like we have cases where we say it blows up, but then we also say the length scale vanishes, and like you said it to 0 in other cases. What's the difference between?
No. Sorry. You just made so the continuous in a continuous phase transition. The feature of there's lattice. I'm gonna draw 1D, but whatever. I can talk about epsilon as this cutoff scale, and then now everything is dimensionless. My 2-point functions are dimensionful, right? But it will be function of L over epsilon, or I can think of it as the number of sites. Good. Okay. Now, correlation length, you could view it as a length as a number multiplied by this. So there is if you look at the correlators far away, past a certain point, the connected correlator disappears. That means that basically there's no entanglement from here and there, roughly speaking. There are no correlations. And entanglement, that's also a fact. Now, what happens is that as you tune the theory near criticality, you separate these guys apart. The correlator, the connected correlator never vanishes. Previously, it was falling off exponential, which meant that if you went 10 correlation length away, then it would be e to minus 10 suppressed, which is absurdly large, right? But now it's falling off parallel, so we can no longer assume that it's falling off. So the words is that there are excitations or there are fluctuations at all orders, at all distances, right? This is criticality, and the fact the exponents are universal. Now, what was the question?
Yeah, what's the difference between 0 correlation length, like saying there's no length scale?
So 0 correlation length means what exactly? So this is infinite correlation length. They're extremely different. So what is a state? Give me an example of a state that is a 0 correlation length.
Just perfectly disordered.
Yeah. So if basically there are absolutely no correlations at any scale, right? That's an infinite temperature state. Good. If this was a quantum example, somehow oddly the quantum. No, actually, classical example is pretty straightforward as well. Basically, what it says is that if you look at the state of any subset, it will be equal probability for any configuration. That occurs if you have literally infinite temperature, right? In physics, we're always interested in infinite correlation length. Again, don't get confused with topological theories. That's a very different story. I'm guessing that's what you asked.
Yeah.
Okay. So now, and then there is another object. So far there's a critical exponent in the 2-point function of spin. Then there is a critical exponent in the correlation length. There's also a critical exponent in specific heat. And then there's magnetic susceptibility. Specific heat, you guys know what it is, right? Specific heat, how do you calculate specific heat? Yeah. So you start with free energy, right? So you take the first derivative of free energy, log of free energy. Sorry, free energy, that gives you U, energy. You take another derivative, that gives you specific heat. Magnetic susceptibility. Oh, actually, in a first, well, I think I'll say that in a second. This is actually a sign of a second order phase transition, by the way. Magnetic susceptibility, is that intuitive for you guys? What it is just an integral over Sx S0 to connect a piece of it over all space. That is a zero momentum limit of the 2-point function. Take the connected 2-point correlator, Fourier transform it, and look at the zero momentum. It's basically saying that, well, fix one of these guys, calculate the correlation between this, and integrate, move this all over the space and integrate it. So it's a zero mode. This is called susceptibility, magnetic susceptibility. This also has a critical exponent. Near a critical point, a thermodynamic system is described by statistical field theory. Atomic scale Lagrangian might be complicated by the IR, but in the IR, the corresponding variables are described by renormalizable Lagrangian. All right. Now, here's an important thing. Here's a question for you guys. We do take, imagine you have Ising model in 4 dimensions. Okay? Now, imagine there's a phase transition. Okay? At finite temperature. Imagine it's continuous. What could be the quantum field theory that describes it? Whatever it is, it will have to be a Z2 invariant CFT, quantum field theory, right? That lives in higher dimensions 4. We already said the scalar field theory in 4 dimensions, the non-interacting one doesn't exist. So it must be free theory, right? So that is described by trivial fixed point, just based on what RG. Now, condensed matter theorists have a method of getting the answer from the trivial theory. It's called mean field theory. So the mean field answer will get the right answer on the nose. All right, so here's what this story is. Finite temperature classical partition function, 1D Ising model has no phase transitions. 2D Ising model, there's a finite TC, it's an exactly solvable near the fixed point, it's described by 2D CFT, it's called the 2D Ising model. This 2D Ising model is very famous. It's the simplest 2D CFT. It has 3 primaries. It's the simplest minimal model. There's a class of infinite central charge half. It's a very famous theory. Everything about it is known. It's integrable. Actually, this is integrable even away from the fixed point. But 3D Ising model has a finite TC phase transition. Near the fixed point, the theory is this mysterious theory called 3D Ising CFT. It is known to be an interacting theory. We do not know how to describe it. People have done a lot of numerics. There are important experiments, including one in the space station. That's about measuring the critical various properties of 3D Ising model. And today we're going to talk about a potential direction to understand it. Wilson-Fisher. Now, for D larger than 3, as we said, the IR theory must be Gaussian. There are no interacting theories. So the IR theory is trivial fixed point, and mean field theory gets it right. All right. So the degrees of freedom here's a is it good? Are there any questions? So this is Ising model, and from a simple statement, simple one loop calculation of beta function for lambda phi 4 theory for scalar, we concluded that basically a whole bunch of things. We concluded that higher than 3 dimensions, the theory, the fixed points, if it exists, it has to be true, right? But this is a Z2 invariant theory. There's very little symmetry, so we have less control. So let's try to see if we can say more. The degrees of freedom of Ising model only have Z2 symmetry. More generally, there are 2 ways of generalizing this. One thing you could do, I don't have a slide about this, but this is for you guys. Imagine your spin now takes values that are 1 or -1. By shift, you could think of it as 0 and 2 or 0 and 1. Imagine your spin degree of freedom is classical. Takes values from 0 to some fixed number p. Integer, like 0, 1, 2, 3, 4, something integer. And you have a lattice of these guys. Good. The Hamiltonian is going to be a sum over nearest neighbor delta of hi and hi plus hij. H is the height. It's called the height function. So you pick a term if the adjacent neighbors have the same level. Otherwise, there's no. So that is suppressed, right? On top of this, you should assume that nearest neighbors, this is hi is the height for side I, always satisfy this property that at most the height goes up or down or stays the same by 1. It most goes up and down by 1. So this defines a very explicit class of models, right? It's a very, very explicit class of models. These models have phase transitions, fine temperature phase transition. They have a continuous phase transition. There's a CFT that describes the physics of it, and that CFT is the minimal model MPP plus 1. These are very well-known CFTs. They've been classified and they've been. It's very, very explicit.
So that second condition basically allows you to force grain, like if they don't vary.
It's a little bit more complicated than that. I don't have an intuition as yeah, I don't have an intuition. You could, I think you could relax it by making the Hamiltonian a little bit more complicated, making Hamiltonian such that you penalize configurations where the drop is larger. You could do that, of course. And then deep in the infrared, they're just going to disappear. These are minimal models. They're very well known. They're discovered. Everything about them are known. They have to do with integrability. Now, another direction you could generalize this is to say, well, spin is a vector in Rn, right? So Si dot Sj, this is dot, the vector product. So the nearest neighbor is a vector, like say, there's a vector here, there's a vector here, right? This gives you a model that's called the ON model, N vector model. So sometimes this is called, in condensed matter, it's called N vector model. The N equals 0 is self-avoiding walk. It's a beautiful story. You could study this. It's very cute, actually. N equal 1 is the Ising model. N equal 2 is what was called XY model. N equal 3 is the Heisenberg model. N equal 4. Does anyone know what N equal 4 is? Have you heard of these? I think all in self-avoiding block probably. X, Y are also very important. So X, Y has a phase transition, and it has Nobel Prizes were given for that phase transition. It had topological nature. The Heisenberg model is also very interesting. The N equal 4 is super cute. It has a really funny story. Does anyone know what it's related to? It has a fixed point. The theory that describes that fixed point shares a lot in common with the theory of Higgs particle. It's the same universality class. All right. So this is a condensed matter story, and we're talking about everything we've learned about quantum field theory is like has all sorts of interesting applications here. Good. Hopefully, are there any questions? Now, hopefully that motivates you to look at the ON model. We looked at the ON model before as well. Of course, we're interested in spontaneous symmetry breaking, right? These phase transitions. And we saw that spontaneous symmetry breaking occurs in ON model. We did some calculations for this, right? So here's the ON model. It's a vector, the degrees of freedom are a vector, and phi squared is, well, that's what it is, sum of I over phi squared. To describe the spontaneous symmetry broken phase, what we did was that we assumed that phi takes some value, phi classical, expectation value, 1-point function. We expanded around that and expanded the action around this classical value. So what does it look like? What does the action look like? So this is a fluctuation, and this is the 1-point function. Right, we did this with a completely different motivation in the past. I was using this as an example for calculations of effective action, right? But now you can totally see what the motivation for this is from a condensed matter perspective, or from a quantum field theory perspective. All right, so what you end up with is L phi classical plus there's a kinetic term for the fluctuation, there's a mass term for the fluctuations, there's an interaction term for fluctuations, lambda 4, lambda chi 4. Now there's an interaction term. There are these two terms that are important. The chi squared term, this can be interpreted as the phi classical, the expectation value shifting the mass of chi. Good. There's this term. Oh. No, wait, what? No. I'm doing something wrong here. Yeah, what I'm doing wrong is this. But I'm doing wrong is chi. Yeah. There's also this term. Right? No. No. Yeah, sorry. This term is phi classical dot chi squared. That's what this term is. So the terms that are second order in chi is this, which looks like chi I, chi j, lambda phi CL squared minus half. And then there's this term, which has phi CL chi j, phi CL I, chi I. This is diagonal. This is not diagonal. So there's a kinetic term, you end up with this. This is what we call a mass matrix, right? The field, the mass matrix for the field propagating field chi will depend on phi CL. It looks like this. The way we dealt with this, if you recall, was that, well, we picked a particular configuration, direction. We said that, oh, let's just pick phi CL because of the ON symmetry. It's all in the one direction. So it's phi CL 0, 0, 0. And then we split chi into the mode that is in this direction and the perpendicular modes, right? This was a story of spontaneous breaking, and we saw the Goulson boson, Nambu-Goulson boson. In Fourier space, the action takes this form. So here's the Fourier space form of it, right? This means that pi I pi j will pick up a different mass compared to sigma. So if this is the field in this basis, this is what it looks like. What we've done using this choice is we've diagonalized the matrix. But importantly, the one that's in the direction of phi classical will pick a different mass compared to this guy. This is an n by n matrix because pi is a n minus 1 vector, and sigma is just a one mode, single mode. Any questions about this? We're giving time. All right. Good. All right. Now, when we wrote down, sorry, this is an action. This determines the action, which is Gaussian. When we calculated effective action, we saw that the effective action to the one loop order looks like the classical action plus log of the determinant of the derivative of Lagrangian with respect to two field insertions, then higher loops. So the one loop comes from only the Gaussian piece, right? The master. All right, that's easy. That means that the effective action is the classical action, right? Plus half logarithm of determinant of delta. This is the delta ij plus mij squared, right? Good. Is this familiar to you guys? Logarithm of determinant of a matrix is the same thing as the trace of the logarithm of A. Do I need to do it on the board? Is it clear? Okay. If I want to calculate the log of the determinant, I can view it as a trace of the logarithm. Now, this operator is diagonal in momentum basis. So trace means an integral over momenta, and logarithm means logarithm of the eigenvalues. So it's ln of minus p squared plus m squared plus 3 lambda phi CL. That's coming from the sigma mode. There are two determinants here. And then there's another one. There's another, well, this integral applies here as well. There are n minus 1 degrees of freedom, right, from this matrix. Integral over p, logarithm minus p squared plus m squared plus lambda phi CL squared. There are two different masses. Good. Now, these integrals are divergent. As usual, we have a set of tricks to deal with these divergent integrals, right? So let's say it's 4-dimensional, 4 dimensions. So there's the structure of this divergence is, well, first of all, this guy is dimension full. So I need a scale, right? So let's divide this by m squared, some large m squared, some dimension full thing that I invent. So we want to integrate this. The way we integrate this is that we write down logarithm as derivative of with respect to alpha of this guy to the power of minus alpha at alpha equals 0. That's just an identity. We used this kind of tricks before, a different disguise. Now, here's where the trick is. You take the integral inside the derivative. So you say this is del alpha of the integral evaluated at alpha equals 0. Okay? Now you introduce a cutoff, a sharp cutoff on k squared. So I'm not saying that this is the only way to do it. Every such integrals we have, sometimes, like I do it in different ways of regulating so that you get familiar, you get more used to it. Some people have a policy of sticking to one regulator. I actually think that that's not necessarily a good thing because it makes it hard to follow other people's calculations. Next time I teach QFT, I will include a simple lecture on what dimensional regularization is. It's actually kind of intuitive, but well, that's for another time. So, all right, you can introduce a sharp cut of lambda and take the derivative. This is just simple algebra. This is the answer. 1/32 pi squared. There's a term that's lambda 4. You could have guessed that, right? You could have guessed that it has a lambda 4 term. Can you? It looked like what? What are we integrating? We're integrating on d4 of k of log of something over k, some function of k over f squared or something. This has k4 term in it. That's pretty obvious, right? Then there's a lambda 2 term, and then there's a log term. Right. So you do this, and this is the form of it. All of these will need to be canceled using counter terms. I'm gonna do normalized perturbation theory in one shot. It's a Gaussian theory. It's pretty straightforward. We did it before with a little bit more detail, but at this level it's pretty simple. What you do is you add the term which is a1, a2 phi CL squared, a3 phi CL4 to capture the divergence of this. The counter terms cancel the divergences, and we're left with a renormalized effective action that looks like this. It won't be very different. Basically has the following form. It's the classical, this is the density, I'm right, Lagrangian density. Effective action density or potential, effective potential. So there's a classical one, value. Yeah. Plus 1/64 pi squared. This expression. This comes from performing this comes from the determinant of the sigma mode. This comes from the determinant of the pi modes. So I've now integrated the fluctuations, the quantum fluctuations, corrected my effective action to the one loop order, right? So this as a function null of phi CL. If you don't include the second line, if you vary that thing, you're going to get the classical equations of motion. But if you add that term, you're going to get the one loop corrections, right? That's just coming from the fluctuations, Gaussian fluctuations. All right. This is what the potential looks like for phi CL, right? That's what we start with. Are there any questions about this calculation? Notice that we're doing this calculation near a Gaussian fixed point. So both MR squared and lambda R are small. Okay. We treat both of them as couplings. All right. So what was the Kalan-Siemens equation? I'm just going to write it this way. This is the Kalan-Siemens equation. Right? We need to take this effective action is the integral over the effective potential. So forget about the integration. I just write down the kernel here. We need to take derivative with respect to m of phi CL. M is appearing here. We need to take derivative with respect to lambda. We need to take derivative with respect to m squared. These are the terms that appear here. And that will have to cancel this term. And then there's a beta function. Well, the beta function sits next to this guy. All right. You do that. M del M of the effective potential. Of course, the only M dependence is the one loop is in the one loop correction. This is what it looks like. Del lambda of nu is half phi CL cube to power 4 plus higher order correction. That's our M squared than lambda. So press this. This sits next to what? This sits next to beta function. This sits next to m squared. So this is, I'm keeping order m squared already. Good. I already know that beta function also going to have lambda in it. That's why I cut them off here. Now, just plug these back into this equation for Kalensi-Manzik. You obtain and demand that you get, it becomes an algebraic equation. You have the following expression. You obtain at this order minus 1 over 30. Let me, 1 over 32 pi squared times this thing, nm4 plus 2n minus 2 lambda phi CL squared. Is it clear what the calculation is? So I'm just plugging these three values inside this equation. This differentiation I could do explicitly, right? And I have to get something equals 0. This is what it looks like. What is the physics of nm4 term in effective action? That's a constant term in effective action. What does it tell you? No, it's field independent. It's the energy of the vacuum that's getting shifted, right? We are gonna deal with that at some point. We're always gonna at this in quantum field here at this level, we just discard all the contributions to vacuum, right? Okay, so that term goes away. Now you should get cancellations at every order for phi CL. So the only terms that are phi CL squared, one of them comes from m squared del m, right? This term. That should cancel the term from m squared, the other guy. And then there's a phi 4 term from here that should cancel this. These two should cancel. That will tell you what beta functions are and what gammas are. That's it. So we calculate the beta function and the running of mass sorry at one loop. If you want them to cancel, you should satisfy these two equations. You find that beta of lambda is lambda squared n plus 8 over 8 pi squared. And then gamma of m is minus n plus 2 lambda over 8 pi squared. What should you pay attention to here? This. What does this mean? It means that in 4 dimensions, so what we calculated was that we calculate the effective action, beta function. We calculate the beta function for an ON model in 4 dimensions, and we found it to be positive. So this theory is doomed in 4 dimensions, the same way as scalar field theory was doomed. It's a generalization of it, but it can't exist. There's no interacting theory. Good? Does anyone have any guesses at where I'm going to go with this? Something interesting happened compared to a previous example of a free field theory. This is the key idea behind Wilson-Fisher fixed point. So what did we do previously in the scalar field? We did Wilson-Fisher. Wilson-Fisher did what? Wilson-Fisher came from the realization that this is positive in 4 dimensions, but in 4 minus epsilon dimension, there is a linear term in epsilon with lambda next to it that shifts this. You end up with another fixed point, right? Can you guess now what's happening? The problem with that was that epsilon had to be small. And what does it mean to work in 3.99 dimensions? Not a very sensible thing to do. However, if you work in 4 minus epsilon dimensions here, calculate the beta function again, you find minus epsilon lambda, the same contribution we found before, plus n plus 8 lambda square over 8 pi square. So now the Wilson-Fisher fixed point is at 8 pi squared epsilon or plus n plus 8. Can you, well, I've written it. Can you see what happened? This fixed point, you could be in 3 dimensions and have this fixed value to be small. So you could have a full arc because of n, because thanks to n. At the large n, what happens is that you could, previously I said epsilon is small, so that I had to say it's small so that I stay within perturbation theory at one loop. I could trust it. Because lambda star, which was the new fixed point, the value of the coupling at the new fixed point, had the only small parameter in front of it was epsilon. So I had to be near 4 dimensions. Now I find it to be 8 pi square epsilon over n plus 8. So I can take n to be large and take epsilon to be 1. Right? This is the so-called Wilson-Fisher fixed point that you analytically continue to epsilon going to 1 or even epsilon going to 2. You could do that too. This is the magic of symmetry. Right? Symmetry allowed you to have a controlled flow. Now, is this really all clean? It can be made all clean, but the presentation here has a whole bunch of loops in it, holes in it, right? In particular, the gamma functions we're dealing with, right? So epsilon came out of expansion of the gamma functions. These gamma functions have, at integer values, have a different behavior. So it's a limiting thing that you have to be careful with. But Wilson-Fisher fixed point is this. Now, it turns out that you could use large N ON model to calculate various critical exponents in a controlled sense, sending epsilon to 1 for large N ON models, right? And try to match it with the experiments. What we see. The theories are non-perturbative, but there's a pretty decent matching. The large N approximation gets you very, very neat answers. It is a very beautiful story. It's a long story, and I'm not an expert on this, but there's an intuition that's out there that says that in a large N model, if you did a calculation that for some fundamental principle was N independent, that calculation often could be trusted and matched with theories that don't have large N. And this principle has been checked over and over again. It's not the first principle, but it's some sort of intuitive thing that's come out of the calculation. So Wilson-Fisher calculations are very helpful. All right. You could also, the gamma, we also calculated it. Yeah, so Wilson-Fisher, for example, will tell you that this anomalous dimension nu takes this value in D equals 3, epsilon going to 1, and large N. This is the answer. I'm not going to explain the large N expansion of gauge theories or anything. Okay. Questions? So this is Wilson-Fisher. These are large N theories, and we managed to make sense of, thanks to large N symmetry, we have some sensible RG flows from a UV trivial fixed point to some interacting fixed point, all within perturbation theory at one loop. Questions? Actually, I'm not gonna say this either. All right, I'm gonna stop here and say a few more words about the examples that you have so far. Are there any questions before I go on? If you hadn't seen this, it should be shocking. The mysterious aspect of this is dim reg, right? Now, dim reg is one way of regularizing quantum field theory, these integrals. There are a couple of other ways of regularizing quantum field theory integrals. Another one is called zeta function regularization. Another one is called the heat kernel. So heat kernel and zeta function regularizations are mathematically very, very solid. There's a very beautiful theory of it. And it's understood, as far as I'm under the impression that zeta function regularization is the same thing as DIMREG. So DIMREG is a repackaged physicist, poor man's way of doing the zeta function regularization. So there's a lot that is going on over there. It's all relying on analyticity. All right. So at this point, what are the theories that you do know? What quantum field theories do you know that exist? What have we constructed? QED was dead, right? QED didn't exist. What did we have? We had lambda phi 4 in d less equal to 3. That theory exists. Actually, well, so the 2D Ising model, 2D CFT, we found it. This is a particular two-dimensional theory that exists. It has central charge equal half. This is a very, very, very simple theory. The XY model, sorry, am I remembering this correctly? Yeah, so the 3D Ising model we have not established its existence. However, for the ON versions of it, we know that it exists through Wilson-Fisher, right? I believe this is correct. XY model has a fixed point that is described by C=1 boson 2D CFT, I believe. In 2D, in D equal 2. So the structure I want to point out is that first, all the examples we found are lower dimension. In 2 dimensions, you have a bunch of examples. I also give the examples of minimal model, just casually mentioned it. Why you could have expected these 2D theories to exist? The structure diverges. Well, actually, for one thing, the divergences get worse in higher dimensions. In scalar field theory, any potential was renormalizable in 2 dimensions, right? So that's a good start. And there are lots of theories that exist, and there's a whole zoo of such theories. Anyway, it's a long story. In 3 dimensions, so far you have a single theory that you know, this theory. You know another theory, actually. The ON model that we just discussed. And del D less than equal to 3. So ON model, the vector model, just gave you a large class of theories that exist in D equal 3. At large n ON models, you know what they are, right? So this is the level of sophistication that we are at. We haven't managed to construct any examples of 4-dimensional theories or higher dimensional theories. Good. It's generally believed that quantum field theory in higher than 6 dimensions, space-time dimensions, must be free. That we could also argue for. I almost argued for that before. Anything you write down is going to be irrelevant. Any interaction term you write down, but that's not a solid argument. But anyway, all right. Any questions? So today we saw a whole bunch of such examples. The next lecture, we're going to give you another set of examples, the so-called nonlinear sigma models. So these are the linear sigma models. This is a large infinite class of theories that exist in 3 dimensions. I think at some point, well, once we're done with RG, then we're going to talk about gauge theories. We're going to spend a lot of time, almost the rest of the course is about gauge theories up to standard model. Gauge theories is when we construct the very first examples of 4-dimensional theories that exist. So this story doesn't get you 4D yet. Nonlinear sigma model is a funny cheat. We'll see. All right, any questions? So now, historically, it should be clear to you guys why, until the discovery of asymptotic freedom, the fact that QCD or non-abelian gauge theory exists, people were very close to abandoning quantum field theory. This is in the late 60s, early 70s, abandoning quantum field theory for particle physics. It was more than clear that it's very good for understanding phases of matter, phase transition, phase of matter in condensed matter physics, lower dimensions. But whether there existed a theory, 4-dimensional theory, was nobody had a single example until gauge theories came along. Interacting theories. Now you want gauge theory QED with mass is dead. All right. That's where I'm going to stop. Any last questions?
When was the development of CFT in terms of like?
Oh, it's actually after this, historically. So the development of to understand what conformal field theory could mean, you have to study the representation theory of SOD, 2, and that was done by physicists. It was known in math, but was imported to physics and studied by people like Mach in early 70s. So
after this standard model?
Sorry?
After the standard model?
So standard model is around the same time as well. So I don't really, I might be, yeah, like
it's around 60.
Yeah, standard model, the anomaly cancellations, and those are like late 60s. But yeah. Standard model anomaly cancellation was crucial for it. We're gonna hopefully get there and describe that. If anomaly cancellation hadn't happened, standard model would not just make sense. However, the issue of whether it's like renormalizable, whether it's renormalizability was also proven, but whether the beta function, the story of beta function was a big deal, right? But sorry, what was I going to say? Yeah, so the higher dimensional conformal field theory structure was laid there. Then in the 70s, the only examples of this was in 2 dimensions, there was a 2D Ising model, there was a free field theory, there was a Liouville theory, a whole bunch of theories. 3 dimensions is this mysterious 3D Ising model that people could numerically calculate. This around the same time when lattice gauge theory came along. Lattice methods came along too, so you could, Wilson suggested you could use computers to calculate these things, so numerics started coming in. The leap in understanding conformal field theory came along in the 80s when Zamolodchikov, Belevin, and those guys, group of Russians, they understood that 2-dimensional CFDs have an infinite dimensional symmetry group called Virasoro. And then representation theory of Virasoro is a lot more complex. A lot actually, because it's infinite dimensional, it's very large. 2D CFD has an enormous symmetry that is more constrained, and you could do better. So there's a central charge, there's a parameter in there called central charge. All 2D CFDs that are modular invariant, central charge less than 1 were classified. There was a modular invariance principle. A lot develops. And it's fair to say that up until maybe 7, 8 years ago, higher dimensional CFD methods were not discussed much. Like CFD, even when I was a grad student, even like early days of my postdocs, most discussion of CFDs, all the beautiful structure of CFDs was about 2D CFDs. And then in higher dimensions, people thought that these are very formal equations and there's not much to take out. There's not much juice to take out. I think around 2014 is when people realized that there numerically showed that you could use the so-called crossing equations of higher dimensional CFDs to learn about 3D Ising model and different things. So they started using the so-called bootstrap methods as a competitor to Monte Carlo. Monte Carlo is this numerical methods. Anyway, so a lot has happened since, come a long way. All right. Any questions? I do have to say one more